Great, all right. So we are actually very excited about all of you being here this afternoon. Today is the day, sort of the culmination, almost the culmination, of a 4-week course, which we call Momentum. And this class was actually sold as Explore the Brain-Computer Interface. Control the what? World with your brain, with your mind. Okay, they're not going to really do that today, but they're going to do some things that are really close and very cool. And so we've had 34 students in a class working with TAs and a lead instructor and a whole bunch of support systems, including corporate sponsors, to bring today to fruition. So you're going to hear some lightning talks from 8 teams, and then you'll also be able to participate in a poster session from those same 8 teams to learn about what they did over the last 4 weeks and to actually learn how they put together this prototype to do just what we just discussed. So, welcome to this event. I think you'll learn a lot. I think you'll be very, very impressed with what our first year and second year students have accomplished in a very short amount of time. And so, we also welcome your participation and your feedback. There will actually be an official Q&A at the poster session, so you won't actually do a Q&A after the lightning talks. So write down questions that you have. Those of you who have agreed to give feedback to the teams, please feel free to complete those sheets as they go through this process so that you can give them helpful, constructive feedback that will enhance their academic performance here at MIT and beyond. So, without further ado, I'd like to introduce the lead instructor for the class, Professor Joel Volman, who is a professor in our Course 6, which is Electrical Engineering and Computer Science. Please welcome Professor Volman.
I'll also not walk around nearly as much as I normally do to make your life easier. So I want to tell you a little bit about our competition that we've been undertaking for the last 4 weeks, and I'll start with a movie, because a movie illustrates what we're trying to get at. This is a little video from 60 Minutes.
I can close it and open it, and I can go forward and back.
That is just the most astounding thing I've ever seen. Can we shake hands?
Sure.
No, really.
Yeah.
Like, come right over here?
Yes, you come over there.
Okay.
Let me grasp your hand there. There we go.
Oh my goodness. Wow.
And I can do a fist bump if you'd like.
That's amazing. What are you doing, Jan? What's going on in your mind as you're moving this arm around? What are you thinking?
An example of assistive technology, assistive neural engineering in particular, where this woman who's paralyzed is using a set of electrodes that are implanted into her brain to control this robotic arm. And this is very much in line with what the students have been doing with our competition. This field of neural engineering is focused on sensory motor functions. So either being able to replace or repair a motor deficit, so being able to move your arm, which is a motor outcome, or to be able to replace lost sensation. So if someone is deaf and you create a cochlear implant, that would be an example of sensory motor neural engineering. And this year in Momentum, the competition has been to create very much something like this. Okay? Instead of directly recording from the brain, they're going to record from their muscles, but they're still recording intents. And the idea is to perform tasks that allow someone to host a dinner party. So very complex tasks where someone will have some intent, and that'll be measured using a set of muscle sensors, and that intent will be decoded, computed upon, and used to actuate and control a robotic arm with a hand attachment that will then perform complex tasks. This is an active area of university research that people may spend their entire PhDs on. Of course, this is MIT, so we'll do it in 4 weeks. There's a set of tasks that are based on, with points based on difficulty, accuracy, and time in some cases. You can come tomorrow afternoon to see the competition itself. I'm going to tell you a little bit about the different tasks in the competition, but really the most important thing to do is to introduce the staff. Our TAs, our illustrious TAs are seated all the way over here, and they're mentioned all the way on the left here. We have 6 TAs who really helped out with the teams, seeing what the teams have produced is probably as both scary and satisfying to the TAs as it is to the teams. So what have we been trying to do? We're trying to create a muscle-based brain-computer interface, okay, that allows us to perform enabling tasks for someone who's paralyzed at a dinner party. And these are the 5 tasks, from writing invitations all the way to serving food. I'm going to tell you a little bit about each task because the teams will talk about it and what the point distributions are. And I'm going to turn it over to Chandler and we can get started. So for instance, we have a task which is writing invitations. So there's going to be this little robotic arm with a hand put over here on the table and a marker over here, and they have to somehow figure out how to get that to pick something up, pick up the marker, and then write various things. So the simplest thing to do would be to write lines and curves, or you could do something more complicated like shapes. You could have randomly generated words, so someone might say, write the word coffee, and can you write that word using this muscle-controlled arm, and there's a point there. And then an open-ended drawing here. So what can you do in terms of controlling this arm to draw something? Another one is call guests on a rotary phone. Okay, so this is actually pretty challenging. I put a picture of a rotary phone here for those who don't recall. But you remember you have to sort of go, put your finger in here and then turn it all the way to the metal thing and then let go. Okay? And so how do you actually make a robotic arm hand do that? It has to remove the receiver, dial numbers, and then pick up the receiver after dialing in order to be able to talk. That's a very complex set of tasks, very under-defined, and we'll see how our teams do in terms of doing that. You have to arrange the place settings. So given plates and utensils, can you pick them up from one location and deliver them to another location in the right orientation, for instance, for the utensils, and within a specified location? Okay, so within the boundary, you get a certain number of points. If you're entirely within it or partially within it, you get points for orientation. As an extra challenge, if you can take a napkin and put it in there and even fold it, you can even get more points. And then making coffee, okay? So making coffee is a pretty complex task. If anyone who does that at home would know. So for instance, picking up the paper cup, turning it upside down or right side up, getting coffee into there, and putting it on the serving platter and serving it are the main tasks, with additional optional tasks like adding sugar, which comes in the form of cubes and must be crushed, to adding creamer, which comes in a sealed little creamer thingy, and mixing the coffee, okay? And then there's delta points, for instance, if you spill something or you destroy, for instance, the creamer pack, that's not good. If you have a creative method of doing things, that can get you extra points. And finally, you want to serve some food. So this looks kind of straightforward when you start out. You have a bunch of platter with a bunch of food on it, and you want to put them on here, and then take this loaded up plate and move it over there. But some of these foods are easy to move, like for instance, a cheese cube. Some of them are more challenging to move, like a scoop of gelatin. Okay, so you think about how you would control that hand in order to squeeze, but not squeeze too much. You think about feedback control. Okay? And then transferring this plate to either the bullseye or outer zones with fewer points as you go farther away from the middle. So those are the tasks that we'll hear about today and we'll see tomorrow. I'm very excited. I'm going to turn it over to Chandler now, who's going to take us through the presentations.
Yes. Hello, everyone. Thank you for coming. I'm not going to stand before you long. My name is Chandler Douglas. I was one of the program assistants for the course. I'm very excited for you to be here. Before we move forward, if we could we have 4 very esteemed judges here to give rankings to our teams. If you just want to wave your hand really quickly, say hi. Won't make you introduce yourself. But we're very glad here they're part of the acting members of Board of Industry Partners who help support me and make this possible. Just a quick tidbit about what's going to happen today. The students are about to give lightning talks, about 5-minute presentations in which they're going to really intrigue you and tell you the best aspects of their design, of their team, and why you should come visit them. And so I'm sure it's going to be brief, it's going to go really quickly, and you'll have lots of questions. And I ask that you write those questions down, that you remember those for when you go out into the poster session. And so they'll have detailed posters talking about the design, the project they're doing. They're willing to interact with you, more interactive than just a question and answer session. I do have one request during the poster session. The judges are here. They'll be walking around with their brown clipboards, and they'll be me in my purple shirt. When we come to a poster, we just ask that you kindly just step aside. We have 8 teams in a short amount of time to go through. And so teams have worked very hard to prepare a short presentation for the judges, and we'd love to be able to see all of them in the time we have allotted. So now, without further ado, we begin the lightning talks.
Thank you. Thank you.
Yeah, you're on.
Thank you so much, Chandler. And thank you to everyone at Augmented for putting on this event. We'd also like to thank all of you for showing up to this. I'm Charles Bachmeyer.
I'm Sabrina Ibarra.
Along with our other 2 teammates, Aaron Lynn and Mustafa Negim, we make up Team 1 and Team Armed and Dangerous.
So first, the dangerous part of the team. Charlie was in charge of the electrical engineering aspect of things, so he hooked up the servo motors to the servo shields and to the Arduinos. He also built the graphical user interface, or the GUI. Aaron was in charge of calibrating the servos and writing the code to interpret the EMG signals. I was in charge of the inverse kinematics to move the robot. So how that works is I made a function where you give it the desired values or the desired set of coordinates, and it outputs the degrees to the robot and tells it exactly where to move. I also integrated Aaron and Charlie's code with mine to form the main program. And Mustafa was the mechanical engineer of the group, so he helped build the robot, and he also built the base for the robot, and he is also the operator. So for all of you who have seen the Imitation Game, we actually nicknamed our robot Christopher after the machine in the movie. And we decided that Christopher should have 3 main priorities. He is easy to operate, so he doesn't place an undue burden on the operator. He has a graphical user interface that tells the operator exactly what the robot is doing, and he is capable of smooth and precise motion for the tasks such as writing letters and serving appetizers.
Now, expanding on that first point, we always wanted to make sure that the operator was thought of first. So we wanted to put very little stress on them, which made us use, at max, 4 sensors. We have different modes set up so that at each time, the 4 sensors could be doing a variety of different functions, maximizing our potential ability just using the 4 max sensors. The sensors are also very non-intrusive, and they're very movable, and we designed this as an assistive technology so the sensors can be moved to meet the desired needs of the individual. We also, taking the sensor readings, we want to just focus on high impulses, which would reduce small static noise, such as if he just twitches, which would cause the robot to just twitch out, and would be very dangerous for both the robot and the user. And it would also eliminate the need to be constantly flexing to control the robot, and it can be quick and very seamless for the user. Now, we want to focus more on the code than requiring the operator to have a lot of training to use this, which required us to design a graphical user interface to tell the user all the information that the code is currently taking in and reading. Now, this provides the user with what mode they're currently in, and the user interface adapts to each mode and will tell what muscle is doing what in that current mode, so the user doesn't have to keep track of it. And we want to go, and for certain functions such as writing, it allows a picker tool, which makes it very simple to choose letters, and the letters are arranged in most frequent use, and the user can easily reverse or leap to certain letters, which would require a maximum amount of time of 2.5 seconds per letter to write. And we wanted to go with a very simple design. As Chandler stated, we have a very small time frame to do this project, so we went with a very simple design, and it also leaves very little distraction for the user in the final competition.
So for the smooth and precise motion, the robot is actually incapable of moving jerkily. It will only move smoothly from place to place, and we've programmed it to only move at a steady rate. So it won't move too fast or too slow, and so this provides additional safety for the user because, for example, if the robot were holding a cup of hot coffee, you would not want it to just spill it just because of the small twitch. It also provides additional safety for the arm, so that the arm cannot break itself. The values actually go to null, and if the arm overextends, it will just shut down. And then, so another side of that is that it can handle very delicate tasks. Even though precise and perfect servo calibration is near impossible, what we did for writing letters and stuff like that was we pre-warped the values that we gave the robot so that when the robot warps them, they come out perfectly normal. So it will write with pretty good handwriting.
Well, thank you for your time, and we look forward to answering any questions you may have in our presentation. Thank you.
Hello and welcome. We are Build and Lift B&L. My name is David Bustillos.
And I'm Daniel Boucher-Belson, and we'd like to talk to you a little bit about our project. So, the challenge we were given was to imagine we had lost the use of an arm, and to build a machine that would allow the user to reclaim some of their lost freedom. So, in order to host a dinner party, we created an arm using muscle sensors that could accomplish tasks related to the dinner party. And although this one isn't directly usable by someone who doesn't have the use of their muscles, the methods we utilized are analogous to those you could use in a brain-computer interface using EEGs instead. So we used electromyography, EMG, which reads electrical impulses from the muscles, and we take that output and use it to move the arm. And in order to keep the controls simple, we use a bunch of different end effectors or hands instead of creating a ton of different modes for the machine itself. These are the members of our team. David and Olivia worked on the mechanical engineering side of things. They machined, implemented, and made the different end effectors or hands. And Kelsey, Bernard, and I worked on the code. Kelsey took the EMG readings and turned them into XYZ movements. I took those XYZs and turned them into servo angles, and Bernard took the servo angles and gave them directly to the robot.
So when we started, we wanted to make the robotic arm better than a human arm. We wanted to take advantage of the mechanics of the actual arm. So we decided to hack the wrist servo so that it would rotate 360 degrees. To do this, we took out the potentiometer and replaced it with two 2.2 kilo ohm resistors. Now it moves freely 360 degrees. With this in mind, we made several tasks much easier. For example, the rotary phone, we simply arranged the arm in such a way that it works as a compass with a marker to move the dial. Additionally, with the marker attached on the side, we could use this as a writing utensil to make curves and other complex shapes like circles. To pick up objects, we decided to make a pew chart to determine which end effector would be most effective for our robot. We decided that pincers with felt pads on the gripping surface and a double spatula would be the two best options. We made them out of sheet metal, specifically steel, and made it such that the pincers would be able to pick up small objects and the double spatula would handle big objects.
So the code works in two separate modes, which you can switch between at the press of a button. In one, sensors on your bicep and two quadriceps control the wrist rotation, the wrist angle, and the wrist gripper, respectively. And then at the press of a button, you switch to XYZ control. And we have ours set so that as you flex, if you're above a certain threshold, the arm moves at a constant rate in the corresponding axis. And there's a second button you can press to reverse the direction along that same axis.
So, budget. We set out we were allotted with $500. Now, we used what materials we could find in D-Lab. This included wood for the base, sheet metal for the end effectors, and resistors for the 360 servo. Things that we had to buy included a marker to make the compass, the all-important duct tape, because you can't have a project without duct tape, needles to open creamer, and 4 EMGs. We only need 3 to operate the robotic arm, but we learned the hard way that we need to make sure we connect the right wires to the right batteries and don't fry the board. Sorry. 3 aspects distinguish our group: low cost, mechanical advantages, and ease of control. The Low cost would make this affordable for the most people, and that's important considering the people we want to give this to. Mechanical advantages include the 360-degree wrist and the modularity of the end effectors. The ease of control only involves 3 EMGs, so the user only has to use 3 muscle groups. Additionally, toggling to the wrist control, you can control it in such a way that you have fine motor skills.
Thank you for listening to our short talk, and we hope you give your questions to the rest of our group at the close of presentations.
Hello, we are Team 2, Bullet Train Homies, and our team is comprised of Yen, Nenye, and Agagu, and Marina Martinez, myself, Eric Delos, and Sienna Reyes. So our team was, we split up into 4 roles, and so Nenye was our hardware specialist, and he made sure that he did a lot of the math for the robot, make sure that all the hardware parts work together with each other, and also designing like the robot and the way that it would move, and doing all the equations to make sure that it stayed within balance. Morena was our communication specialist, so she made sure that all the channels of communication stayed open between people, and she also made our poster and our presentation, and she also soldered anything that we needed. Sienna was our treasurer, so she got all the parts that we would need for our project, and she also put it all together. And I was the software integration, so I took the code that everyone built and I put it all together and I made sure it all worked. And we were all the point people for this, so no one only did this thing, but we were the one that was mainly in charge and oversaw it and made sure that it got done. And so for phase 1, we thought about what was it that we wanted the robot to do. We wanted it to be able to do all these tasks and be able to do it simply and easily. And so we thought of 2 different strategies to go about it. We could have either one, that the robot arm mimics the human arm, or 2, that we use the human body as a joystick, and the coordinate systems that we put in through like our muscles, the robot arm would move to those. And from that, we decided to go with strategy 2 because we thought it was easier to implement, and it was much more adaptable to everything else. And our concept for strategy 2 was to get the different muscle groups, and for each muscle group to be a different part.
So phase 2 was our programming and testing part. We ended up splitting this part into 3 different sections that we needed to complete. So this graphic describes more in detail what we needed to do. So we split this up into, the first part was making sure that the signal from the sensors would go into, could translate into coordinates that the robot could identify. Then the next was doing, making the coordinates and translating those into angles that the motor would need to go to. And after that, getting the motor to do what it actually needed to do and making the robot move. We split this, we ended up starting with group 2, and we split up all the coding between all the groups, so we actually had like a pretty functioning robot within a day. We just needed to get the sensors to work, which was phase 3. So in phase 3, we decided to test different muscle groups and see which ones gave us the best signals. So our robot is able to pick up very, very, very clear signals and responds very well to signals that we get it to do. For our, the competition, and then we worked on making sure that Nenye, our driver, was able to actually get everything to work, and he was very comfortable with the robot and making sure that our robot did what it needed to do for our competition. And these are more pictures describing this. That's what our product looks like.
We'd like to give special thanks to the Office of Minority Education, the Momentum staff, the Momentum teaching staff, MITRES, D-Lab, and the Cypress Engineering Studio.
Once again, we are Team Bullet Train Homies. We would love to answer any of your questions during the poster session, and we look forward to talking to you.
Hello everyone, we are Team Delos, and our arm's name is Apollo. The members of Team Delos are Chris Compton, course 9, Julian Delarme, course 6-3, myself, Fabian Germa, 10B, and Paul Tujuchi, course 1. And now Delarme will discuss more of our design process.
So the four of us focused our design around the user. We wanted our arm to be as easy to control and command as possible. So to do this, we wanted to adapt a modular design that was easy to change on the fly. Something that can be edited, added, or removed onto the program at will, because we don't know everything about our user or their needs. So we want it to be easily changeable as a user changed or as their needs changed over time. On the programming side, we did a few things. First, we converted our EMG signal to binary, on or off. This made our design very robust and less susceptible to noise, which we found is very prevalent in the EMG signal. So we can easily tune the EMG just by changing the thresholds, what means off and what means on. And this made it easy to switch between users, which of course changed the signal, or if the battery was dying and the gain was different, etc., etc. It was very easy to change the threshold on the signal. So by having 3 EMGs, we were able to create a very simple binary table, as shown in the bottom left, and map simple functions to each different command. To implement our modular design, we have different modes for all of our functions and tasks for the dinner party. By separating this out, it was easy to change each one individually without affecting the rest, and it was easy to add more if there was a secret task or if the user changed and you needed to do something else, or remove if you no longer needed it, or edit it if you changed from, let's say, a rotary phone to a cellular phone. So by using these different modes, it was really easy to change the binary table and the mapping to something different on the fly. And of course, you always have a backup plan because you can simply change the mode to a manual mode, which we programmed, which made it easy to control the arm manually without any special input from the program side. To do this, though, we needed to change the servo controls, which required angles, to something that was easier to affect, like XYZ coordinates in space. So to do this, we used inverse kinematics, and Fabian will discuss that in detail.
Yes, as you see over there on the image on the left, we had to use inverse kinematics to determine the angles at each joint. And so in order to use the coordinate mode, we had to have each angle. So the way we started doing that was by calculating A, which was distance between the base and the gripper. And once we found A, it was very easy to use trigonometry to define each angle. So after we found the angle, it was easy to give our program a single XYZ coordinate, and then it would easily translate it into angles for the servos. But once we started playing around with our arm, it was very obvious to see that you could get to a single point using multiple methods. And so we had to do another analysis, a torque analysis, to determine what the most effective and efficient method would be to get to a single point in space. When we started doing the torque analysis, we noticed that the torque of the wrist was only dependent on the angle of the wrist. The torque of the elbow was dependent on the angle of the elbow and the wrist. And the torque of the shoulder was dependent on all 3 angles, the elbow, the shoulder, and the wrist. And so after we were done doing our calculations, it was very easy to notice that to pick up anything, the most effective way would be to use our elbows. And it makes sense because normally when we pick up things, we use our elbows to pick them up, not just the wrist or the shoulder. And so from there, we could implement that into a code and find the most efficient way to pick objects up, which tends to be half the challenge here. And now Julian will discuss more of what we've learned during this process.
So this was a long and fun IAP for everyone on Team Delos, and we learned many new things, including team software design and development. We learned how to program the Arduino to control 5 servos on the arm. And of course, we learned a lot about team time management, which was very, very important in this competition. So thank you all again for listening.
We are Team Delos, and we look forward to answering your questions during the poster presentation. Thank you.
Hello, I'm Alicia Alexander.
I'm Hugh Day Williams, along with our teammates Michael Pfeffer and Rachel Hausman.
And we are Team Harmony. So our strategy for creating our muscle-controlled robotic arm was to first approach, brainstorm, and then finalize our plans. With our approach, we decided to break down each of the tasks into several different stages, and then classify those stages into an axis of control, going from moving forward and backwards, left to right, or just with the wrist rotation.
Now, for our brainstorming, we all started off individually thinking of A, how we wanted to control the robot, and B, any attachments we might need to meet the challenges. We then came together, critiqued each other's ideas, and ended up with one final strategy for our robot, which will be to use 2 sets of electromyography boards, or EMG boards, that's kind of a mouthful, in order to control the robot in 2 different axes at once, either forward or back, side to side, and then up and down in a separate mode. This will allow us to reduce costs by using fewer EMG boards. It's a simpler to set up the apparatus and simpler for the user to interact with the robot. And it also allows us to very quickly switch between modes, and therefore we don't lose any functionality in the arm.
So we went from this idea to then make a prototype design. With our prototype design, we first started with taking the idea and making it into code using inverse kinematics. With inverse kinematics, essentially, instead of working each of the motors on the arm, which would be difficult and for the user to work with, we made it so that if you have a desired endpoint or a desired axis to work on, then you could simply work with that axis.
We also use the EMG boards to allow they read the potential in a person's muscles. Therefore, when you flex and increase the potential, the arm will move accordingly.
Also, you'll notice with the arm that the gripper only moves, opens and closes, and moves in that particular axis of rotation, which is not the full flexibility of an arm. There are no fingers. So to give it a little bit of help, we had to add physical attachments to help it out and make it a more natural process.
Now, we decided to split up the work between the 4 of our people in order to make things more effective. And this was based on our previous skill sets, but along the way we also learned a lot too and had to pick things up rather quickly in order to complete our timetable.
I primarily worked with the hardware additions and these attachments that would help the robot, and also with the safety to make sure that no one was hurt or killed in the process of making this arm. Michael Pfeffer was our chief circuit analyst and also worked with most of the math for the inverse kinematics, and so he made sure the circuits were safe to use and that everything went smoothly.
Personally, I work with interfacing the EMG with the Arduino and making sure that when you flex, the arm actually moves. And I also was our team treasurer in made our purchases for the apparatus and attachments for the arm. And Rachel Hausman worked with coding all of the automatic functions of the arm, in addition to keeping our team on track and our timetable, making sure that we meted our deadlines and kept to a good pace. Now, given I was the team treasurer, I kept track of the budget. So our main 2 expenses were EMG boards and EMG shields. It's a very small distinction, but we found that the EMG shields were more reliable in giving a good signal and were also more cost effective, so we ended up going with those. We also had several more minor expenses that we just needed to make the apparatus function. Ultimately, out of our $500 budget, we spent $466.
So with this entire process, the biggest challenge for our team was the robot. None of us have any experience with robotics, and we each have separate experiences with parts of building a robot. Some of us had experience with electrical engineering, mechanical engineering, and computer science. So for the majority of this experience was team dynamics and taking each of our abilities and skills and working them together to create this project.
And we also did a lot of work with time management and really prioritizing what we needed to get done. Given that we only had a month to complete what seemed like an insurmountable task, we had to organize what was most important for our robot to have based on the point allocations and the challenges. And given that we're getting towards the end of this lightning talk, I hope you'll also be able to learn some presentation skills as well. Now, through the countless hours of work of our team, through hours of imagining, designing, and a lot of troubleshooting, we got everything to work in harmony. I know that was cheesy.
We'll help you visit our table and learn more about exactly how this robot works and how we're so confident about the competition tomorrow.
Thanks a lot.
Welcome to the grand view of the latest technology. It is a robotic arm that will help disabled users regain their function for their daily life.
The robotic arm that we've been working on this past month features a user-friendly control interface, specific control of the movement, orientation, and position of the robotic arm, and a united team available for customer support.
Specifically for this competition, our robotic arm will complete a series of tasks to plan a dinner party.
But before we delve into the specifics, let's meet the team behind the machine. This is Stratton.
I am the project leader. I also work on a PowerPoint presentation along with building the robot. Let's meet along.
I've been in charge of code and electronics, and some of the things I worked on were brainstorming and coding the movement and the control of the robotic arm.
Another team member that we have, her name is Wendy.
And Wendy was our treasurer and hardware leader and co-leader, and she focused on making sure that our finances were at point at all times, and she also worked on the build of the robot. And our final member is Arthur Williams Jr.
He is the co-coder, and he also worked on the electronic components of the robotic arm.
So So today we're going to look at the strategy that we're using to approach the momentum competition, our prototype, our code and calculations, assumptions we've made, modes that we pre-programmed, safety guarantees, resources we used, and the timeline of our project.
Our strategy for the competition is to practice, practice, and practice, and attack the lower level tasks first. During the days leading up to the competition, our strategy was testing and then debugging, testing and then debugging. So our tasks include writing invitation, making calls. Joe already gave you an overview of the task.
So this is our prototype, and it's a very simple design. It consists of 2 EMG boards, 1 for each arm, and then we also have 5 buttons and a slide switch to switch between modes that we will talk about in a bit. And as Joel talked about it, the EMG boards amplify the signal, and then that goes into the Arduino, which acts as sort of like the brain of the robotic arm, and then we can use that into the code, put that into the code, and execute the user's desired position. And this is sort of like an outline of our code. First, we have the user set the mode that they want. Then they put in the EMG input, which consists of flexing either arm. Then we take that into the code, and that's very mode dependent. Finally, we perform inverse kinematics calculations to find the desired angles for the different servos, which are sort of like the joints of the robotic arm. And finally, we convert those angles into pulse width modulation signals, which the servos then read and go to the desired position.
As Ivan mentioned, our robotic arm features a couple of modes. The first mode will control the grip.
The second mode focuses on the twist aspect of the grip.
The third mode focuses on the orientation of the grip.
The fourth mode is X movement, and that refers to the axis from the robot towards the tasks.
The fifth mode focuses on the Y control, which is the direction perpendicular to the task.
Mode 6 is the height of the robotic arm, so that chooses where the grip is. And mode 7, 8, and 9 are basically like a combination of the previous modes, and those we implemented to give the user a bit more control over the arm. They're specifically useful in the momentum tasks, such as the writing task or the picking up task.
For our prototype, we made a few assumptions. The first assumption is that the user has control of their arms, and the sensors are within a reasonable tolerance. And the last one is the user has to have sufficient practice.
And our design has a couple of safety guarantees. We have a capacitor as well as a current resistor, and these are to make sure that the user is in no electrical danger. And we also have a sturdy build to ensure that the robotic arm will go to the user's desired position with no alteration.
Our budget started with $500, but we only used $167 for sensors and replacement parts.
And this is just the general outline of our project. We met all our deadlines. It shows our progress, milestones, and whatnot. And we used the Gantt chart in the smartsheet.com application.
And of course, we only had a month to build our current prototype. If we had more time, we envisioned even a better robotic arm, maybe making it wireless, lightweight, and even a friendlier user interface.
Thank you very much for your time, and we look forward to your questions in the poster presentation.
Thank you.
Hello, I'm Chandler Squires. I'm a freshman studying computer science and mathematics.
I'm Michael Forsman. I'm also a freshman studying electrical engineering and computer science.
We're here today representing Team 6, the right hand of God. Our other team members are Trin Nguyen, who is studying biological engineering,
and Jonathan Harvey Buscal, who is studying electrical engineering. So I'd like you all to think about your morning.
Raise your hand if you brushed your teeth. Be honest.
Okay, almost all of you, right?
So think about doing a simple task like that without the use of your hands.
It's absurd how many people don't think about something like this. Where in the US, 2.8% of the population
6.7 million people
report difficulty picking up a pen or a glass.
Given such a staggering statistic, the 4 members of our team were drawn to this class due to our interest in assistive technology.
So with our limited experience and about 3 months of the prototype and design, we decided to set out and create a brain-computer interface using EMG.
As we began strategizing, we learned a lot about each other and our strengths. Mike here was very instrumental in the robot construction, early on showing his familiarity and competence with Arduino projects. He was also the ideas guy he allowed us to have a lot of options for our strategy going forward.
Jarden was our lead technician, and without his help in the electrical engineering side, I don't think we would have actually gotten anything done. Where Chandler here, and yes, he is a very funny guy, but most of his work was in the coding and the debugging realm, and really without him, we probably wouldn't have a working code right now.
And last but not least, we have Trin, who early on established herself as the responsible one of the group. She called all the meetings, she prepared a lot of the presentations, kept us on track, and she was a very enthusiastic learner, picking up stuff from each of the fields and implementing it in our design.
So our design has 3 ideals. We wanted to keep it simple, coherent, and limitless.
To keep it simple, we decided to do inverse kinematics instead of resolve rate motion control, which is an idea we had been playing around with. This allowed us to keep all of the computation on the Arduino and not have to interface with other hardware. We also decided to use only 2 types of sensors. That way we could allocate more time to figuring out how the pressure sensors and EMGs responded to signals from our bodies.
To keep in line with simplicity, we are only using the few sensors, but we're doing it and we're taking the signal from it and we're processing that on top of what the boards already do. So we're doing that in both the hardware and software way. And we're coding everything so that you can adapt to any task.
So in our design process, we tried to keep it very logical. First, we wanted to establish basic control over the robot with keyboard input, making sure we could do everything that we wanted to do before worrying about interfacing with the human body. Once we got that done, we moved on to using sensory data, processing it and making it usable. From there, we fabricated additional hardware to be used for specific tasks, and only then did we interface it all into one robust design.
So, as you can imagine, we had a lot of problems. First of all, how do we get noise out of the EMG signal? The snow day, for example, is also a huge problem. And then eventually, we broke a lot of stuff. We did fix it, no one is hurt, and it did not set us back too long, but it prevented us from testing quite a bit.
So some unique aspects of our design are a modal interface that allows us to easily reuse input for different tasks, such as moving in 3D space, flexing, rotating, and gripping, and even motion and cylindrical coordinates. Another unique aspect was our multi-use tools, which allow us to extend the reach of the gripper and are easily removable.
And then as far as signal processing, we took a hardware and software approach to this, where we have another sensor giving us data in conjunction with our code, which will limit some of the noise.
In the process, we learned a lot of technical skills from electrical design, programming, and mechanical engineering, and a lot of non-technical skills, such as teamwork, time management, and organization.
And most importantly, Murphy's Law. So, again, thank you for being here. And I hope you have some questions, because I would love to talk to all you guys. I believe Jonathan and the rest of our team would too. So come see us.
Thank you.
So I'd like you to take a moment to imagine a world in which we could have this woman and all the women like her and give them the ability to have back control of a limb. We are Team Stratton Oakmont. My name is Lordique. This is Jihan. That's Dylan. And that is Jennifer. So we started off with a vision. We asked ourselves, who did we want to help? How did we want to help them? And why were we doing what we were doing? We wanted to give all the people with sensory motor deficits a robotic arm to enable them and to alleviate the pain and loss that they feel when they lose control of their arms. How did we want to do that? We wanted to use a non-invasive brain-computer interface. So we obviously didn't want to open up our heads and implant electrodes, because that's painful, although we do love momentum. And we wanted to do that in less than 15 days. So you can see here that we all had our individual strengths, but we just leveraged them all together so that we could have maximum efficiency. And that is a great characteristic of our team.
So based on the vision that we had, we wondered what design would actually make the robotic arm to carry out the task efficiently but with precision. So based on the limitations we had on the budget and the materials that we had, we thought what combination of the autonomous and the automatic control we could use to actually efficiently operate the arm to carry out the task that was needed.
So I just want you to look for a moment, and that is what we started with. That is all we had.
And then our main approach is the modular approach and the two-axis approach, where the first modular approach is dividing each task into smaller modules where the operator can effectively control two axes and to operate the arm. And then the two-axis approach is to have each module integrated with two axes so that the operator can control the two axes and precisely reach out for the objects. And then this is our schematics, where the muscle signals are picked up by the surface electrodes with the EMG, and then it is fed back into the Arduino, and then we program the modules where the operator can actually decide which modules it will be in, and then based on the module, the module is fed back into the Arduino, and then the robotic arm performs what is needed.
All right, so you guys know what our design is. Now we're going to talk about our implementation. So there were two main phases to our implementation. One was that we needed to do sensors and modules. So sensors, we had to buy additional EMG boards because the ones we were given were not, they didn't function for us correctly. So we had to buy more. And we also had to code all the modules so that we could break down the complex tasks into usable, or into things that we could control via EMG. The second phase of our implementation was mechanical augmentation. So our robot was not actually capable of doing most of the tasks that were required. For example, dialing a phone, you need to have a special key to dial. So we augmented our robot by giving it a specific base with holes for tools so that we could pre-program the robot to grab the tools. And so we wouldn't waste time having the user to do that kind of thing. So these are our results. Hopefully they'll speak for themselves. We prepared a video for you. Well, it was really awesome. We'll show you later. So basically our robot can write. It can precisely control and place objects. It is capable of getting tools automatically, very rapidly. It is very responsive to our commands. So, we are Team Stratton Oakmont. We succeeded by modulating the tasks, leveraging our strengths, and creating a fully capable assistive robotic arm in less than 15 days. Thank you.
Thank you.
Wow, that was really great. Can we have a hand for all of our 8 teams, Momentum teams? Now, the great part is that the fun is only halfway over. So we're going to transition to a hostess session in which you're able to interact with the different teams. They can tell you their stories, they can tell you their designs, and answer any of your questions.